Okay, so today we'll be talking about Mosfets. And so Mosfets stand for metal oxide semiconductor field effect transistors, which is just a big name, but in a little bit we'll understand why some of these terms come about. And so, but before we go into any more of that, let's talk about the gate capacitance, right? Or also called a MOS capacitor, or metal oxide semiconductor capacitor. So the first question is, what is a MOS capacitor? That's the first question. And so we'll draw the basic structure of a MOS capacitor. So here's the basic structure. We have a gate. It's also just the metal contact, right? It's made of polysilicon, just because it provides a very, very good conduction, just like a metallic element does, or a metallic contact, metallic plate. Then we have an insulator. A lot of times silicon dioxide is used because of its good insulating qualities. And then we have the substrate, which is P minus silicon. It just means it has some hole carriers, but the concentration is quite low. Okay, so now the MOS capacitor has 4 distinct regions of operation. In this case, this MOS capacitor right here is acting in the flat band operation because there is no applied bias. There is no voltage that is applied across the capacitor, right? So it's right there. So MOS capacitor has 4 distinct regions of operation. Alright. And you can already see that this is going to act as a capacitor. Some charge is going to be stored in the upper plate, and some charge is going to be stored in the lower plate. In this case, the metal and the substrate, respectively. Or the gate and the substrate. Okay, so the different regions of operation are the following. So you're going to have flat band, which is the one that we just mentioned above. So it'll be flat band operation. Then you're going to have accumulation. That's 2 C's. Accumulation or linear operation. And then that is under negative bias. Then we're going to have depletion operation, and we'll expand into these different cases in a little bit. Depletion operation. And then that is under moderate. Positive bias. Then we're going to have inversion operation, and this is the one we care the most about. It's the most important one. Inversion operation, and this is under what we call higher positive bias, and that will become clear in a little bit. And so you get in this inversion operation there is 3 sub regions of operation, which is the weak inversion, which are the weak inversion. Then you have moderate inversion. And the most important one, strong inversion. That's how we use our transistors most of the time. Okay, so now we'll expand into some of these regions. The flat band operation was already described in this case right here, where we have no applied bias, right? And so there is no charge. It's just like, no, I mean a capacitor without any voltage across it. It's just not doing anything, right? There is no charge stored. The other one that is a little more interesting is the accumulation or linear operation. So let's talk about that one. So okay, so let's draw. So if we applying a negative voltage, remember what we said before, and let's draw the basic structure for this. So here is the basic structure, right? And so due to the negative voltage that we are applying, the electrons are flowing from through the wire down to the metallic contact and are getting accumulated here in the gate, right? This starts pulling some of the positive charges in this doped silicon to the top of the substrate. This is the substrate. I think I forgot to probably write it. Right, and so in reality you have some negative charge stored here and some positive charge stored here and an insulator in the middle, so we have a capacitor. And so let's write out what's happening. So due to the negative charges at the gate, holes are attracted to the top of the substrate, like we said. Okay, and then note the following, right? At the top of the substrate, we're going to have a small region that is charged, that has a lot of holes, right, laying around. Kind of like a little small channel. We call this a little, or we can say that we have a small p plus region, right? A region that has abundant holes in it, right? So this can also say, so we can conclude the following. In the accumulation region, decreasing the voltage at the gate induces a proportional accumulation of holes. So this is the key word, and that's why it's called like that, this region of operation, at the top of the substrate that I was explained before. And so we said that proportional accumulation, that proportional is the keyword, right? That means that we have a linear capacitor, right? Remember, you got that C equal to the change in charge per change in voltage. And if this ratio remains equal, right, if we change the voltage by 1 volt and then the charge increases by x coulombs, and then we change the voltage by 2 volts and the charge increases at 2 times x coulombs, then that means that the capacitor is linear, capacitance doesn't change, which is a representation, or it tells us that this structure right here is a linear capacitor, or that the MOS capacitor operating in accumulation region behaves as a linear capacitor. Okay, so now that was a little bit long, but the other ones will go a little bit faster. So now the depletion operation And remember, the depletion operation happens when we are applying the MOS capacitor under moderate positive bias, like we can see here, right? So once we do that, some of the electrons start flowing out of the gate of the conductor, right? And we end up with positive charges accumulating at the gate, right? And that starts to repel some of the holes that are mobile in the substrate, and start leaving some fixed charges behind, right? Like here. But as we mentioned before, for the PN junction capacitance, this capacitance as well, right here, is non-linear, right? Because you have a limited amount of holes in the substrate, right? So in the beginning, as you increase the voltage in the gate, some of these mobile holes are going to get out of there, and then the charge is going to be proportional. But then as we reach a limit, and the number of holes available in this region is very, very small, pushing that voltage high even more is not going to make much difference in the amount of charge stored. And so you have a non-linear capacitor. So let's write that down. So due to the positive charges at the gate, these ones, holes are repelled from the top of the substrate, leaving negative charges behind, negative fixed charges. That's very important. And then little caveat, so as we have seen from before, the depletion capacitance is non-linear. As there are a limited number of fixed charges. Okay, so now let's talk about inversion operation. That's a more interesting case. At the end, we would like to get into strong inversion so we can understand Mosfet operation. Okay, so inversion operation. So something to talk about is that inversion happens when we keep increasing the gate voltage. There are no more negative fixed charges in that region, so thermally generated electrons begin to be attracted to the top of the substrate. These mobile electrons move to the top of the substrate, generating a layer of N-doped silicon, right? Thus, the term inversion. You're generating an N-type region within a P-type material. Okay, so let's write that down, and then we'll make we'll graphically explain what's happening. The gate voltage and there are no more negative fixed charges, so thermally generated electrons are attracted now these mobile electrons move to the top of the substrate, generating a layer of n-doped silicon and thus the term inversion. That's where it comes from. Right? And so because you're generation of an n-type region within p-type material. Right? So what I want you to do is we're going to do it graphically, and later on we're going to read this and then see that this follows. So weak inversion, the first case. Right, so let's take the graph that we had before. Okay, so here's the case for weak inversion. So as you can see, we're putting more positive charge in the gate, right? And there is only a certain amount of fixed charges available in this region. So what's happening is that we're attracting some thermally generated electrons up here, right? And so the condition for weak inversion is the following. And then it's when the number of mobile electrons is lower than the number of fixed charges we are in weak inversion. Alright, so here is the number of fixed charges and here is the mobile electrons. Right? As you can see, there is way more fixed charges than mobile electrons, therefore we are in weak inversion. Okay, now the next one is a moderate inversion. Okay, so let's draw the okay, so here is the graphical view, and note what's happening. As we increase the gate voltage, we have more positive charge stored in the gate, right? We'll start pulling more negative charge to the top of the substrate, but this negative charge now is coming in the form of thermally generated electrons. And so, but now look, the thermally generated electrons are the same in quantity as the number of negative fixed charges. That's the condition for a moderate inversion. So let's write that down really quick. So when the number of mobile electrons is equal to the number of fixed charges we are in moderate inversion. Okay, so now we get to the more interesting case, the one that we care about, and is called strong inversion. So let's see, strong inversion. So we put it there, we go. And so that is which happens as we continue increasing the gate voltage. As we mentioned before, this is the most interesting case, because this is how we use our transistors or MOSFETs. Okay, so let's draw the visual model, right, and note what's happening here. So you're increasing the gate voltage, so you're putting more positive charge into the gate, right, which is pulling more negative charge into the inversion layer, what we call it right here. But note, most of the charge is coming in the form of electrons, thermally generated electrons, right? And you can see that the number of electrons are way more than the number of fixed charges. And now you have this inversion layer or conduction channel that is generated at the top of the substrate. So let's write the conditions for strong inversion. When the number of mobile electrons is more than the number of fixed charges, we are in a strong inversion. Probably write that in blue. There we go. Okay, so now a concept that sometimes is kind of important, and I think it's very nice to see where it comes from, is that a lot of times when we're talking about transistors, we talk about the threshold voltage, or VT, right? And so here we can explain what the real meaning of VT is. So what is the threshold voltage? It is the voltage at which the inversion layer charge dominates, or in other words, when we start getting more mobile electrons than fixed charges. At the point where we go from moderate inversion over to strong inversion. That is what's called the threshold voltage, the voltage that is required to generate that effect. So let's write that down, and you should probably remember that when you talk about a transistor MOSFETs. At which the inversion layer charge dominates or, in other words, when we start getting more mobile electrons than fixed charges. Right? At the point where we go from moderate inversion over to strong inversion. Right? This is called the threshold voltage. So that's how you write it. Okay? And so this is the building block of a MOS transistor. Now we have all the tools we need. So, so the MOS capacitor in a strong inversion is the building block, as we will see in a little bit. Okay, so now we have all the tools to start talking about MOSFET. So we'll start talking about MOSFET transistor. So apart from the gate, which is the system for how the gate works, we already have that. We just explained it. Now we need the drain and the source. So that's what we will add next. So now all we need for a MOSFET is to add a source and a drain, right? First we'll talk about a MOSFET transistor that is called an N MOSFET. I'll explain a little bit why, actually right now. The reason why it's called an NMOS, this is NMOSFET, stands for NMOS channel transistor. It is because the inversion layer or conduction channel is made of electron carriers. That is, electrons carry the charge in N MOSFETs. Okay, so let's write that down, and then we will draw our model and explain it visually. It's made of electron carriers. That is, electrons carry the charge in N MOSFETs. Okay, so here's the visual diagram of an N MOSFET. And so what you have here is the MOS capacitor, the one that we've been talking about right here, right? You got the gate, the insulator, and the substrate. And then to manufacture the source and the drain, what we have is N plus silicon that is put into the substrate right here for both the drain and the source. But then you see that there is an intersection between the gate, the MOS capacitor right here, and the source in this little piece right here. And then you have an intersection too between the MOS capacitor and the drain right here, right? And that will become very important later on. Okay, so now that's the diagram for an N MOSFET. Now let's draw the diagram for a P MOSFET, and then for the next section, what we will do will be that we will put different biases to this transistor and see how the device performs. Right? So now let's talk about P MOSFET. The reason why it is called an N and PMOS channel transistor is because the inversion layer or conductive channel is made of hole carriers. That is, holes carry the charge in P MOSFETs. Okay? So let's write that down. The mechanism for working these two devices is very similar. It's just opposite. That's why when you're working with equations, they tell you that all you need to do is just apply the same equations that you would with an N MOSFET for the PMOS. Just change, instead of VGS, change VSG, right? And that will do it. Okay, so now the reason why it's called a PMOS channel transistor is because the inversion layer or conduction channel is made of hole carriers, that is, holes carry the charge in P MOSFETs. Okay, so let's draw the visual diagram really quick. Okay, so note what we have right here. The MOS capacitor is still here, just like for the N MOSFET, right? You got the gate, you got the insulator, and you got the substrate. But now the substrate is made of N minus type silicon, right? And the source and the drain are made of a P plus type silicon, both of them. The intersection between the MOS capacitor and the drain and the source is still there. So the two models are very similar. Okay, now we get to the fun part, right? We start putting some voltages to these devices, see how they perform. So MOSFET behavior under applied bias. Right? This is what we care about. I will take the case of an N MOSFET. As I said before, the operation of these two devices is just the same. It's just that one of them is conducting through holes and the other one is conducting through electrons. Under subthreshold. Okay, so subthreshold is one of the regions of operation. Sometimes it is also called cutoff. And then the conditions for that region are just that the gate voltage is less than threshold. Remember how we talked about the threshold voltage? Here is where you can apply it. Okay, so here's the visual model. Okay, so the first thing to note is that the MOS transistor is operating in weak inversion. Remember what it means? It means that the fixed negative charges right here are a lot more than the electrons, just these two right here, right? And so also note that the source and the drains are grounded, right, are tied to ground, which means that the extra electrons here from these N plus materials are flowing directly to ground right here, right? That means that now we have a p-n junction here from the N plus type material to the p minus type material, right here and right here. What this means is that there is no conduction channel. Like the fact that we are in weak inversion means there is no conduction channel, right? So even though we apply a voltage here, there is no carriers to generate a current, right? And so you don't have any current flowing through here, right? That's why the MOSFET is in cutoff, right? So let's write that. So looking at this, we see that the MOS transistor is in weak inversion, and if we remember, that means that the fixed negative charges are a lot more than the number of electrons. Also note that the source and drain are grounded, so the extra electrons from the N plus material flow to ground, leaving a region of positive fixed charges. These ones right here, and we have p-n junctions from bulk to source. Bulk is also the substrate, it's the same thing, and bulk to drain. Another thing to note, so note also that since there is no conduction channel, because we are in weak inversion, even if we applied a voltage difference from drain to source, from here to here, there will be no flow of current. In reality, there is a very small quantity. If you apply a very high voltage from drain to source, you still have a few carriers here, right? And due to the high electric field, they're gonna, if any of them gets in there, it's gonna go, right? So it's gonna be very small current, if any. So, except nowadays they are using some of these devices in sub-threshold for minimization of power consumption. And that's how they will operate. But for our purposes, we can think of the transistor as being off. Okay. All right. Okay. So now an interesting case will be to see what will happen if we keep increasing the gate voltage above the threshold. Remember? So we take the transistor or the MOS capacitor from moderate inversion over to strong inversion. So now we get a conduction channel going on. So increasing the gate voltage right, so that's the next case. And so let's draw the model. Okay, so how are we biasing this device? So right now we're putting into the gate voltage is more than the threshold voltage, assuming that the threshold voltage is 0.7, just a value that I choose, right? You can have, Mosfet devices can have sometimes threshold voltages of 400 millivolts, 500 millivolts. It just depends on how it is built, right? Okay, so as we said before, increasing the gate voltage above the threshold puts the transistor into strong inversion and establishes the conduction channel right here, right? So now you got a channel that is full of mobile electrons, right? So in theory, if you can induce an electric field to get some current flow throughout that channel if you put a drain to source voltage, right? So let's write that down. Actually, before that, let's explain one quick concept, and is the VDS saturation, or sometimes called the overdrive voltage. It is given by the gate to source voltage minus the threshold voltage, right? It is the drain to source voltage that is needed to put the transistor into saturation. We'll discuss a little bit more about that later, but just to let you know. So increasing, let's write down what I just said. The gate voltage above the threshold, and I like to write write what I'm saying just so that it gives you some time to grasp the concept. I know how hard it is to time yourself when you are trying to explain a concept. You might get it, but the person that is listening to you might not, right? But if you write it down, you give people some time to understand it. And establishes the conduction channel. This means the transistor is on, up until now we have not been changing the drain to source voltage. Okay, so now in theory we can induce an electric field to get some current flow through that channel. For example, a way of inducing the electric field would be we could apply drain to source voltage. Which is what we will be doing next. Okay, so now what happens if we apply a small drain to source voltage? So that's the main question here. Okay, so this is how the transistor will look like. Alright, just a quick model. And then you get the gate voltage, you get the fact that it's an N MOSFET, that's why you get the arrow in there. And now, as we said before, we'll get some current flowing since there is a drain to source and there is a conduction channel. Drain to source voltage and the conduction channel. Okay, now let's draw our visual diagram. Okay, so here it is. So first, the biasing conditions. We are applying a gate voltage of 1 volt, right? We are applying a drain to source voltage, since the source is grounded, of 50 millivolts. That means that this S is the drain to source voltage is much less than the overdrive voltage. So let's go back and remember what the overdrive voltage was. The overdrive voltage was the gate to source voltage minus the threshold voltage, which we defined it to be 0.3 volts, and it was the drain to source voltage needed to put the transistor into saturation. So we know the transistor is not in saturation because it's less than that, right? And it's much less than that, which means it puts the transistor into deep triode region, right? So now let's note what's happening, again in a qualitative view. So note what's happening, and it looks complicated, but it'll get much better. Okay, so 3 effects, right? The first one is you get a conduction channel which becomes asymmetrical, right? You see now, before, when the transistor was on and without a drain to source voltage, it was just a conduction channel that didn't have any slope to it. Now we get this kind of like triangular conduction channel right here, right? Then the next thing that happened was that the depletion regions at the drain to bulk junction increased in size, right? More fixed charges were uncovered, right? You get those. And the third thing is that there is now an established electric field from drain to source, which creates a drain current, right? Going from right to left. So let's write those things down, and then we'll explain how that went about. So basically what this is that we run the experiment, and this is what we got. Now we have to make sense of that. And we will in a little bit. Okay, so that's the first thing that happened, that we saw. Second thing was the depletion regions at the drain to bulk junction right here, increased in size. Why? Because now you're getting more electrons flowing out, which means that you are uncovering more fixed charges, right? And so you're uncovering more fixed charges in the other side as well, right? Because it's repelling those holes, right? So you're getting more uncovered negative fixed charges, and the depletion region increases. Okay, I should have explained that a little bit below. So more fixed charges were uncovered. Okay, so and the third one is there is now an established electric field from drain to source. Okay, so now making sense of this, right? How did this happen? Okay, so the first thing, first, the higher potential at the drain, due to this voltage, repel the mobile electrons in the conduction channels that are closest to the drain, right? So some of the electrons that were here, they were swept to the left because of this higher potential, right? They were repelled by it, and so therefore that's what creates that effect. And so let's write that down. So the higher potential at the drain repelled the mobile electrons in the conduction channel closest to the drain. Okay, so that's the first explaining that we have to do. The second is what I explained before, that is that since a higher potential was applied at the drain, BD, more electrons left the N plus material, leaving more positive fixed charges uncovered, widening the depletion region. So let's write that down. And covered, widening the depletion region. Okay, so what we really did here is that we put the transistor into the deep triode region, which is what we explained before, of operation. And it's also called the linear resistor-like region, or the linear transistor region, right? Because small changes in VDS generate proportional changes in drain current. So let's write that down. So the triode region is called the linear resistor-like region. So that means that small changes in VDS generate proportional changes So you could ask, is it possible to use the transistor in this region to simulate a resistor, and the answer is yes, but there is some caveats, right? It's very hard because that region is very, very small, you know, as compared to, say, the saturation or just the triode region. It's a very, very small region. So if you increase the drain to source voltage by a slightly higher amount, then you get out of that region and the transistor is not operating linearly anymore. Okay, so now let's talk about the next topic, and that is what happens as we keep increasing VDS. Right? We keep increasing VDS. Let's write that down. Okay, so now again we got the transistor like this, and you got VDE, ground, you get the fact that it's an Mosfet, and you add the gate and the drain voltage, DC. So now what we're modeling here is the triode region. Okay, so now let's draw the visual model. Okay, so here it is, and let's note the biasing conditions, right? So what we have here is a drain to source voltage of 200 millivolts. We have the gate voltage still greater than VT, still being 1 volt, and then we are in triode region. Since we increase VDS, VDS is now just slightly less than the overdrive voltage or the saturation voltage, right? So let's note what's happening. So I'm going to be writing as I speak to make it a little bit faster. So this is the results that we see when we run the experiment. So while the conduction channel became more asymmetrical, the conduction channel still exists. Still there, right? From drain to source, from here to here. That means that we still have free electrons. Okay. Second thing that we see is that the depletion regions and the drain to bulk junctions increased in size as expected. And then the last thing that we see is that since the applied voltage is greater, the induced electric field is now stronger, right? Since the drain source voltage is greater, then the electric field is now stronger, meaning that electrons in the conduction channel are moving faster. Okay. Therefore, the current is now greater. Okay, so what did we really do here? So let's write that. So what we really did here is that we put the transistor into the triode region. Operation. Okay, meaning that as we keep increasing VDS, the current does not increase proportionally, but increases by lesser and lesser amounts. Right? So the transistor is operating non-linearly. I have a little graph here, so it looks something like this. Actually, more like this. There you go. And then you got VDS in this side, and you got ID in this side, right? So as you increase VDS farther and farther, the slope is changing. So it's operating non-linearly. Okay, so why? It's kind of like the answers that we would like to know. So note that the number of electrons in the rightmost part drain side is very small, right? Which means that for further increases in drain voltage, while the electric field is increasing, the number of available electrons is decreasing, and therefore we get very little increases in current for further increases in drain to source voltage. Drain to source voltage. Alright, so now the most interesting case here is the saturation case, when we operate the transistor in the saturation region, right? So the question we'd like to ask is, what happens if we increase VDS above the saturation or overdrive voltage, right? So that's the question we'd like to ask. And so here's again our little transistor in the high level view, and now we're gonna draw our visual diagram. We still got the ID going on. Okay, so here is the diagram, and let's note that the transistor is operating in saturation region because the drain to source voltage now is greater than the overdrive or the saturation voltage, right? The gate voltage is still greater than the threshold voltage, which means the transistor is on, right? So now let's take a look at what's actually happening. So when we run the experiment again, what do we get? I'm hoping by this point we are already getting some intuition of how this device works. depletion regions, depletion region at the drain to bulk or drain to substrate junction increased in size. And we know that from previous cases because now we are biasing the drain harder, right? We're putting a greater voltage through there. Meaning all these extra electrons, more and more, are actually going out, right? Which are uncovering these fixed charges, which increase the amount of depletion region, make it wider. Cool. So now, also due to the increased drain voltage above the saturation threshold, the channel starts to pinch off. What does that mean? Well, you can see from here. Before we used to have a channel that extended from the drain to the source, right? There were electrons all throughout that channel. Now the channel is moving a little bit too much to the left, and so now it doesn't reach the drain anymore. So that's what that effect is called, the channel pinching off, right? Meaning we don't have a conductive channel from drain to source anymore, right? And that can be seen from the picture. Another thing that happened, there's still current, right? Even though it's a little bit counterintuitive, it will become way clearer in a little bit. Still current due to the strong field, electric field, from the drain to the edge of the conduction channel. Which strongly sweeps electrons towards the source. Okay. Right? So now you got a stronger electric field pointing from this over to the edge of the conduction channel, right? So even though there is not a conduction channel, if an electron is to be found in this region, which is totally possible because now we got an N plus, a lot of electrons in there, then it's going to be strongly swept across until it reaches this conduction channel right here. That's actually what happens. Okay, but most importantly, note that increasing the drain to source voltage has no effect. This is very important on the drain current anymore. Right? And then here's going to explain why. That is because since further, and this is a very important explanation, increases in VDS tend to decrease the number of carriers close, those ones that are close to the drain, increasing the pinch off region the size of this region right here, increasing the pinch off region, which opposes the flow of current, right? While increasing the strength of the electric field, right? Because VDS now is greater. And that increases the flow of current. These two effects tend to cancel each other out. And leave the drain current unchanged with changes in VDS. Right? So that's very important. Well, now the non-idealities of Mosfets. So the things that we told you a little bit before about the Mosfet operation in the saturation region are mostly true except for one little thing, right? It's because the Mosfet is really a non-ideal device, you know, and so we introduce things in a kind of an ideal manner, and later on we start to make him a little more complex. So this effect is called channel length modulation. And what it tells us is that, well, I mean, the behavior of the transistor in the saturation region is not quite that ideal. I'm gonna go pretty fast over these sections because this video is getting quite long. But you already have kind of an intuition of this, so it's probably fine. The idea. Current does indeed increase slightly for further increases in voltage, right? So it's not that ideal, like we said in the previous figure. So current does indeed increase slightly for further increases in drain voltage, right? So remember how we said before that even if you change the drain to source voltage, current will remain constant because the channel pinched off, and there were two effects that cancel each other out, leaving the current unchanged. Well, we have to add another effect to that, and then that will kind of make it so that the current does increase a little bit. Okay, so let's draw the visual model that we have. And again, let's mention the things that we see when we run the experiment, right? So while the pinch off region increases, so this region right here increases, the length of the conductive channel decreases, right? So now we have more electrons in less area, keeping the width of the channel constant. Keeping the width of the channel constant. What this means is that this increased number of electrons act to reduce the resistance of the conductive channel. So this increased number of electrons act to reduce the resistance of the conductive channel. To reduce the resistance of the conductive channel. Right? This effect is what causes the small increases in drain current. With further increases in drain to source voltage. Right? So now it's not that ideal, and this effect becomes a major concern for short channel devices. Right? So, you know, while what we said before was true, that the pinch off region increases, which tends to oppose the flow of current, and the drain to source voltage is now greater, which tends to generate a greater electric field and try to increase the flow of current. Now there is another effect, right? Since we made the pinch off region greater, right, that means that now we have more electrons in less area, which means that the resistivity of this leftover channel right here decreased, right? So that acts to increase the flow of current. And that one is the one that tilts the balance, and now we have a small change in current for further increases in drain to source voltage, right? Okay, so now another non-ideal effect, which is called the body effect. Okay. The question that we have to ask now is, so we talked about the drain, the source, and the gate, but what about the bulk or the substrate? Right? We haven't talked about that one. We are interested, so in the source to bulk voltage VSB. So for a visual experiment, so for a visual experiment, we will let's set the source to voltage to 2 volts, right? Give us a nice number to run an experiment. And then the other things we're interested on are the following. Let's keep the transistor on or out of sub-threshold on. What that means, remember, is that VGS has to be more than VT and VGS has to be more than 0.7, since this is what we chose our threshold voltage to be, and therefore in VG has to be more than 2 plus 0.7, because the source is now at 2 volts, which means that in order to keep the transistor on, we have to set it at 2.7 volts, right? And so we'll round it up to 3 volts. That should give us a nice round number. Okay, so now also we want to, let's keep the transistor on. We want to keep VDS at 500 millivolts. Okay, so therefore VD is equal to 2.5 volts. We have to keep VDS at 500 millivolts because if you remember, the overdrive voltage or the saturation voltage was set at 0.3 volts or 300 millivolts. So in order to keep it in saturation, we gotta keep it a little bit higher. So we choose safely 500 millivolts, right? Okay, and then finally we want to tie the bulb to ground. Okay, so now we have all the biasing conditions. Now let's draw our visual diagram. Okay, so here is the visual diagram. Now we have always draw, and then here is the source, the drain, everything that we have. The source to bulk voltage is right here. The bulk is connected to ground. The gate voltage is set at 3 volts. The drain voltage is set at 2.5 volts. And so we have our experiment ready to go. And so now we want to know what happens when we actually run the experiment, right? And we turn off on the circuit. When we do that, right? So first thing that's going to happen is that the depletion regions at the source and drain widen, and the amount of fixed charges uncovered increases. Why? Well, I mean, we have the drain voltage, which is now higher, and the source voltage itself is now higher too, right? That means that you're pulling all these electrons from the N+ materials in both terminals, and then you end up with a whole bunch of positive fixed charges in this side, right? And the other side as well. So you increase the width of the depletion region, which is what we put there. Okay, so the second effect is that now that we have more fixed charges, available, we require less mobile less mobile electrons in the conduction channel. Or inversion layer. Right? Since the number of fixed charges increases right here, we require less mobile electrons, like it's saying here, so the size of the conduction channel is a lot smaller, right? And then what that's going to generate is the following. So the third thing is, therefore, the conduction channel weakens and the current decreases. Right? And the fourth thing, in order to obtain the same drain current, we would have to raise the gate voltage. Raise the gate voltage. If we look at this set of results, we would see that increasing the source to bulk potential is analogous to increasing the threshold voltage. Right? Since increasing the source to bulk potential, that means that it's going to weaken the conduction channel. In order to get the same conduction channel that you had before, you'll have to increase the gate voltage. And so what that means now is that and this is what you should take out of this, right? By increasing VSB or decreasing VVS, you can, if you want to modulate the voltage of the bulk, and you will think about in terms of VVS, increase the threshold voltage and then by decreasing, it's actually kind of a fun way to think about it, because you know it's you know the threshold voltage is really dependent on the physics of the device, you know, the number of dopants, the concentrations. But if you can modulate the bulk, right, and you can actually modulate the threshold voltage, the bulk or the source, you can actually modulate the threshold voltage, which is kind of a nice result actually. And they use of that a lot or they have done some research to see how they can actually do that, to operate at lower voltages, right? Okay, and so that's the body effect. Okay, so finally we talk about small signal modeling. So I want to talk about what is it all about, you know, when they told you, you know, do a small signal analysis of this circuit. What are they really meaning? Because I know it's confusing. The first that I thought about it, I didn't know what they meant. I'm just gonna give you an explanation, so next time they tell you, or next time you have to do it, you know it's very simple. What it means is just very simple. And you can use concepts that you're familiar with to understand it, you know. So up until now we have been dealing with non-time, just DC, for all our experiments. I've just been putting DC to our circuits, or to our visual diagrams, voltages or DC voltages, right? But now the question is, but what would happen if we now wish to apply an AC input signal right to the transistor? We know that since the transistor has multiple regions of operation, if we apply a signal with a large AC amplitude, the transistor will be operating in multiple regions, right? So let's write that down and then we'll explain it graphically. We know that since the transistor has multiple regions of operation, if we apply a signal with a large AC amplitude, and I'm using concepts that are familiar so that we can see what is meant. A large AC amplitude, the transistor will be operating in multiple regions. Right? For example, as the gate to source voltage increases, so let me write the circuit really quick. So what we have right here is an AC signal generator driving a little Mosfet, and Mosfet in this case, and then you got VDD, and this is the signal that we're putting in. It's a sinusoid. There we go. And so we have, as the gate to source voltage increases, keeping the drain constant the transistor will go from saturation to triode, and then when the amplitude decreases, it will go back to saturation. Okay? Why? Well, I mean, remember that VDS sat or V overdrive is equal to VGS minus VT, right? And we are changing VGS constantly because we are putting a sinusoid into the gate of this device. So conditions for triode, as we remember, were that VDS is smaller than VOV, right? And conditions for saturation were that VDS is more or equal to VOV, right? So you can see that VOV will be increasing, right? Because VGS is increasing, therefore VOV is increasing, leaving the device in triode region. And once it comes back down, then VDS starts to become greater than VOV again, right? And so the device goes back into saturation. This behavior is very non-ideal and non-linear. Right? Since transistors are themselves very non-linear devices. Right? And so the question now that we are going to have is, how do you get linear behavior out of these non-linear devices, right? Right, that's a big question. And so the answer becomes, oh yeah, so for example, I mean, why do we need linear behavior? Well, for example, we need it for amplifiers. Very important. One big group of that is audio amplifiers, for filters, and a whole bunch of other applications. So the answer to that is, well, we keep the device operating in a very small region of operation, or you can also say that we zoom in on the nonlinear curve until it starts to look linear. That is, we bias the transistor around a certain point in a region of operation, in a desired region of operation, around a certain point, in this case using a DC voltage, and make only small perturbations around that point. Right? So the means is apply a signal with a small AC amplitude. Okay? And so let's draw that. So what we have is this simple, right? You're gonna have negative, positive, and then this is the bias, and on top of that you're gonna put an AC signal. So for example, you can think of the bias, you're gonna put it in the saturation region, And then on top of that, you're gonna put an AC signal that just moves it a little bit around, but doesn't take it out of that region. And that AC signal is, like we said before, very small. And then in reality, remember, you're gonna use some sort of coupling so that you don't mix the AC part and the DC part. So the analysis of the response of the system to this little AC signal is called small signal analysis. Right? Therefore, it's simple, right? We're familiar with AC analysis, right? So small signal analysis is just AC analysis, but little caveat, keeping AC magnitudes small. That's it. That's it. That's the way that you have to think about it. You know, that's all a small signal analysis is. As a conclusion for small signal analysis, so to conclude, we're gonna tell you the most important small signal parameter, the most important small signal parameter for Mosfet, or AC parameter, I like that more. For Mosfets is transconductance, right? That is the change in drain current as we make a small change in a gate to source voltage. So what we want to know is the following. It's called GM, and it is the change in drain current as we modulate, or as we change the gate to source voltage, right? Alright, so here I leave you with a review sheet. So this is just the representation for an N MOSFET. Then we have a P MOSFET, right? And then the regions of operation, remember the cutoff region, or in this case the sub-threshold region, remember, is when the gate to source voltage is less than VT. It means the transistor is completely off, right? There is some very little current, but and there is the deep triode region, when the drain to source voltage is much less than the overdrive or saturation voltage. Remember, this is VOV, and this is VOV right here. And then is the linear region, or the resistor, where the transistor behaves as a resistor in a linear fashion. Then there is the triode region, then where the drain to source voltage is less, just slightly less than the overdrive voltage, and the transistor behaves as a voltage control current source. Then we have the saturation region. This is what's called as the active region, and it's the one that is most widely used, where VDS is more than the saturation voltage, or the overdrive voltage. and there is a low dependence of the drain current with changes in the drain to source voltage. It's used for most applications in digital logic. So that's how the transistor is most widely used. So a few hints: always check that the transistor is not off, right? You have to check that the gate to source voltage is more than the threshold voltage, otherwise the transistor is not going to do anything. Then you go ahead and check the operating region, right? And then most of the time we want it in saturation region. Remember that. If you want a transistor to operate in a linear manner, like a resistor, then maybe you will want it in deep triode region. It's very hard, but if you can keep it within that region, you'll operate as a resistor. So here's a graph, and then is the drain current with respect to the drain to source voltage. So what we have is here is the deep triode region, or the linear region. You can see it's the smallest of the three. Then you got the triode region, and then once you pass that overdrive or saturation voltage for the drain to source voltage, then you go into the saturation region. And here is the little slope, right, that is given by the channel length modulation. Alright, hopefully this video gave you kind of an intuitive view of how MOSFET transistors work. That was kind of the goal.